All right, welcome back, folks. We basically said that we needed to figure out a way to rotate or or flip the spin or the magnetic moment by 90 degrees, right? That's what we needed to do. We needed to go from the ground state where the mu is aligned with B and and sort of tilt the mu into the xy plane where we get an angle of 90 degrees. Once we've accomplished that, then everything is done for us. The spin will just rotate, okay? We call it precession. The spin will just precess, and we get this induction signal for free. So we call it the free induction decay. But we needed to find a way to accomplish that initial spin tilt. So initially we have the situation on the left, okay? But we needed to get to this situation on the right. How do we do that? Well, we have to introduce another B field, essentially. We have to use a B field that we now label B sub 1. And it's here, appears here in the sketch in blue. Okay, so why do we need that? Well, if we only had this new field B1 and not the original field, which we call B0, okay, in purple, then the mu would just precess about the B1 axis, just like before it was going to precess about the B0 axis. Now it's going to precess about B1, but notice that we've set it up such that B1 is already perpendicular to mu. So we should get some kind of precession, right? We should get this kind of evolution where initially the mu is pointing along the z direction, and then over time it precesses and eventually will point in the xy plane. So that's the idea. After a certain amount of time, mu should find itself in the xy plane, tilted down into the xy plane. Okay, so here is another sketch of the same situation. We have the B1 field, we have this mu, okay, that's initially aligned with like along the z axis, but then after some time it precesses, right? And therefore, after some time, it's going to be tilted down into the xy plane. So that should do the trick. But the problem is, and there's always a problem here, there's always a complication, right? It can never be just that straightforward, unfortunately. The problem here is that we still have the B naught. That was the original B field that aligned the mu in the first place, right? And that's usually the strong magnetic field. The B naught here usually is the strong magnetic field, and that is not zero by any stretch of the imagination. As a matter of fact, that is a magnetic field on the order of a couple of Tesla. We'll see later that the stronger that field B naught can be made, the better the instrument that you can build, the more resolution you get. So B naught is not zero. It is a very strong magnetic field. It is there. So we still have this thing to contend with as well. So as soon as B1 tilts the spin a little bit away from the z-axis, immediately this kind of precessional motion kicks in. Okay, and so we need now a combination of this precessional motion that happens a little bit more slowly and this very rapid precessional motion about the z-axis. We need to combine the two. What would that look like? Well, you can sort of probably guess that it might look something like this. Some kind of spiral down into the xy plane. So initially the spin is lined up with the z direction. Okay, so we're maybe here. Okay, the tip of the spin vector is right here. And then we sort of spiral down. As we reduce the z component, we have to increase the xy component, right? Because the size of that mu or the size of that spin cannot change. And so we're basically rotating into the xy plane like that. We're spiraling down into the xy plane. So as seen from the top, this would maybe look something like this. Here we're just projecting down into the xy plane. We're looking down the z-axis, sort of tracing out the tip of the the spin vector. Now, another way to visualize this is by sort of boosting into a rotating frame. So instead of your laboratory coordinates x and y, we're now looking at it from a frame that rotates with the spin. So here I'm labeling these axes x prime and y prime. Okay, these are axes that rotate with the precessional motion of the spin along the z-axis. And so if you're sort of then eliminating this quick motion about the z-axis, and all you're left with then is sort of this tilting down into the xy plane. Does that make sense so far? Okay, so here x prime and y prime, just to reiterate, are rotating axes. They rotate around the z-axis at a speed of omega is equal to gamma times b naught. Right, so as to keep up with the spin precession about the z-axis. Okay, and then we basically are isolating, or we're picking out simply just the motion away from the z-axis, the rotation away from the z-axis. All right, so for this to work, there have to be 3 requirements on B1. So B naught, that's a static magnetic field, a strong magnetic field coupled Tesla along the z-axis. We have to specify what we need out of the B1. Okay, and so the first thing we need out of that is it needs to be oriented in the xy plane. It needs to be basically perpendicular to the z-axis of B naught. Okay, and furthermore, in terms of magnitudes, it's got to be, well, it is simply smaller than B naught, for the reason that will become obvious. Okay, because it needs to be static in the rotating frame. It needs to be static in the rotating frame. Why? Because in that frame, the mu will just precess about that static B1 axis. And therefore, we tilt down into the xy plane. So the B1 has to be static as seen from the rotating frame. And what does that mean? Well, that means that it has to be rotating in the fixed frame. All right, it has to be rotating in the fixed laboratory frame. If it's going to be static as viewed from a rotating frame, then that means that it's rotating as seen from the static laboratory frame of reference. And so this B1 can therefore not be a static field. It needs to be rotating. And furthermore, it also needs to turn off abruptly. In other words, it needs to be a pulsed field. So our whole experiment here is called, that we're trying to gear up for, is called pulsed NMR. Okay? And so here you see the first time that the word pulsed appears. We need that B1 to actually turn on and then turn off a little while later. Why is that? Well, once the mu has rotated into the xy plane, if we kept B1 on for even longer, then it would keep rotating, right? And it would approach the minus a z-axis. So we need to stop that process. When it's actually tilted down by 90 degrees, that's when you want to shut off the B1, because if you keep it on longer, then it will overshoot the xy plane and start heading towards the minus z-axis. Okay, so we have B1, we said B1 has to be a rotating field, okay? But for practical purposes, it is also sufficient for it to be an oscillating field along the x-axis. Let me explain that. So here's maybe a possible mathematical expression for B1. Okay, I'm saying that it's okay for it to just oscillate along the x-axis. I had here unit vector along the x-axis. And here's the oscillating part. If this were to be a fully rotating field, I would also need a y component here, right? So I'd have to add plus B1 cosine of omega t j hat. So it is actually, believe it or not, sufficient to just have the x component and drop the y component. And when you do that, you go from a rotating field to an oscillating field. And that is actually also, going to be sufficient. So if you can manage in the lab to create a rotating field, fine, but it's just typically easier to just create an oscillating field along one axis. Okay, and that omega then has to be finely tuned. It has to be tuned to gamma times B naught, namely that's the precessional frequency, right? That is also called the Larmor frequency. And thirdly, we said we needed this field to be pulsed. So when you put it all together, it's going to maybe look something like this. This B1 field, okay, it's off, then you turn it on. It oscillates, okay, for a certain duration of time, and then you shut it off. How long is that duration of time? I'm going to call it T1 here, okay, T1. Not to be confused with T, which is the period of oscillation, 1 over F. Well, that is just 2 pi over gamma times B naught, as we said before. So there's two time scales now in the picture. There's T1, that's the pulse width, and then there's capital T, which is the period of oscillation. It's 1 over the frequency. All right. So with that signal present, we can move from an initial mu that's pointed along Z to a final mu that's pointed somewhere in the XY plane, okay, and we've accomplished this pi over 2 rotation. Okay, so we call this pulse also a pi over 2 pulse for that reason. We've accomplished a pi over 2 rotation, and the pulse that makes that happen will be referred to as a pi over 2 pulse. So how long does this pulse have to be? We said it was T1, right? But what is T1? Well, a simple argument here reveals that T1 is nothing other than pi over 2 gamma times B1. Okay, so I think you can follow this, right? The angle is equal to omega times T. We know that omega itself is gamma times B1 in this case, because it's B1 that rotates it into the XY plane. And then if I want a theta of pi over 2, well, I have to wait. I have to wait a time capital T1, which is equal to pi over 2 times gamma times B1. All right. So the time, the pi over 2 pulse duration does depend inversely on the strength of the B1 field. Okay. So the upshot is that for a pi over 2 pulse, we need an oscillating B1 field that has a duration of pi over 2 gamma times B1, while the period of oscillation is given by 2 pi over gamma times B naught. We also know that B naught is much larger than B1 because B naught can be a static field. We don't need it to oscillate. So typically it's much easier to make that a very large field. And that also then implies that T is much less than T1. So there's going to be many oscillations that can fit into one of these pulses. Okay, and so the idea is after such a pi over 2 pulse, we should detect the free induction signal, right? Picked up by our coil. So the next thing that we have to look at is that signal itself. Why is it decaying away? We said that the EMF that we typically see looks like this. Okay, so we have this oscillation here. Okay, this oscillation happens at the frequency, the Larmor frequency. Okay, that's fine, but it just doesn't persist. It decays away exponentially. And we call the signal, therefore, free induction decay, FID. But why is it decaying? Well, we have to remember that what we actually measure is the combined signal of many individual spins on the order of 10 to the 24 spins, 1 mole, let's say, of a substance. So a tremendous number of spins are involved here. And we can say that initially these spins in the sample are all doing the same thing. So they've all been sort of rotated away from the z-axis, right? And so now they're all precessing about the z-axis, about the B naught field lines. So here's one spin, okay, here's another spin somewhere else in the sample, here's another spin somewhere else in the sample. So I'm highlighting 3 spins that make up this macroscopic signal that we can measure. Now, if B naught were perfectly homogeneous, then these mu's would just continue, to do the same thing. There wouldn't be any reason for these mu's to ever do anything different. And so we had a perfectly homogeneous magnetic field. We should actually then expect an induction signal that wouldn't decay. But we don't have a perfect homogeneity. So homogeneous just means spatially uniform in this context. There might be some variation, okay, in the strength of the magnetic field, B naught. And if you look closely, okay, the way I've drawn it even, the length of those 3 vectors isn't exactly the same. So we get them more or less the same. That's the B naught, but there is also some inhomogeneity, okay, which I'm labeling here. And that is spatially dependent. Okay, so this little b here is spatially dependent. Here's another contribution that I want to talk about. But first, this inhomogeneity, just small spatial fluctuations in the applied field B naught. It's basically just a feature of the magnet that you're using. It can produce a fairly homogeneous magnetic field. And if you put a lot of effort into it, then maybe the homogeneity is pretty good, but there's always going to be some residual variation, fluctuation, or maybe I should say variation, spatial variation. So that's sort of more of a magnet property and therefore macroscopic. But then there's also another contribution, and I've labeled that B local here. Okay, so that's due to the differing local chemical environments of particular protons. So again, we have 10 to the 24 protons in my sample. Okay. There might also be sort of microscopic variations in field, in effective field, due to particular chemical environments. So this B local is actually quite interesting because electron clouds, for instance, can shield the nucleus from some of the applied field, and to different degrees, depending on the exact electronic environment. So what the nucleus feels in terms of a magnetic field might be different from the applied B naught. It can be slightly reduced by the electrons that are around that nucleus. Sort of a quantum mechanical effect. I'm still recording. No, it's not. I'm going to pause it now. Okay. So we call this the chemical shift. And so this is actually a very interesting phenomenon. It's actually the whole basis for NMR spectroscopy. So a lot of organic chemistry is sort of based on this effect that say the proton, the nucleus, the hydrogen nucleus, will precess at slightly different frequencies. Why? Because the B local is different, okay, depending on what's around that proton. So not all nuclei give rise to the same free induction decay resonance line. There are small shifts in frequency depending on, as I said, the electronic configuration in the electronic environment. So due to this chemical shift, then we can say that each organic molecule has its own unique fingerprint in NMR spectroscopy. So, so this is therefore quite a useful scientific tool, okay, for that reason. So the problem, though, that we're facing is that B inhomogeneous is typically the larger perturbation of the two. So it usually dominates the B local. So what that then means is that the spins will precess, but they soon come out of phase with one another. Okay, and it's due to the non-homogeneity of the magnetic field. So it's an instrumental issue, and it's not as that's not as interesting, is it? The B inhomogeneity, as I call it, sort of dominates over the more interesting chemical shift. And so what we get here is that initially all these spins, now I'm superimposing them all, but these would all be spins somewhere at different spatial locations within the sample, right? I'm just putting them all together here. They start out in the XY plane, completely in phase, okay? And then after they've gone around a couple of times, well, you start seeing some of them sort of, lag behind a little bit, and some others have gone ahead in phase. Let's assume that they're rotating clockwise here in this case. So this one here is a little bit slower. This one is a little bit faster due to the inhomogeneity in the magnetic field. Okay, and so that, of course, just keeps going like that. Okay, if you wait even longer, finally, you get a situation where these spins are all spread out over the unit circle. So then if you add up all of these vectors, what do you get? Yeah. What's the combined signal from all of these little mu's? Well, 0, right? There's no more measurable signal at that point. Okay, and that takes a time of T2 star. This takes a certain amount of time. We call that time T2 star. Okay, so when you see that FID signal decay to 0, how long does that take? It takes an amount of time of T2 star, and we call that T2 star relaxation. But what about the more interesting effect of B local? Okay, well, that would be called T2 relaxation to be consistent. Okay, that's gonna take a time T2, but since B local is less than B inhomogeneous, we also get that T2 is longer than T2 star, and that's really kind of a pity because we cannot directly then measure T2. Reason being is that T2 star process is quicker in squashing that signal. It's just quicker, and we don't have time to observe T2, which is longer. But T2 is the more interesting effect, okay? Because it tells us something about the sample itself, or in the medical context, it tells us something about the tissue itself in MRI. So really, the T2 would be the more interesting thing to observe. So is there any way we can get at T2 experimentally in the presence of T2 star process or relaxation? It doesn't seem like there should be a way of teasing out T2, which takes a longer time, but it turns out that there is. There's a very clever way of doing that, and it relies on something called the spin echo, and that's what I'd like to get into in the next part. Thank you very much, folks, and see you for the next installment. All right.